Hello physics students. Today we're going to be talking about free fall again. Now remember in the kinematics unit, last unit, we learned that when you drop something, everything accelerates at the same rate of 9.8 meters per second squared. That means that if I take two things of different mass, if I drop them, the mass doesn't matter. Any two objects near the Earth will fall at the same acceleration and therefore fall a same distance in the same amount of time. So if I do a little experiment and drop these, what we can see is that they'll hit at the same time. And you can't see it because you can't see the table, but you could hear when these drop, you'll hear them hit the table at the same exact time. So you heard, you did not hear like a delay in impact. And so the question is, why does everything fall and take the same amount of time to hit the ground? And when I ask students that, they typically say, well, because gravity pulls everything the same. And I say, what do you mean the same? They say it pulls it at 9.8. And that's not true. Gravity pulls different things differently. And I could just tell you to imagine the following scenario. Suppose we go out to the parking lot and I put this penny on my foot. And then on your foot, I get a school bus, okay, back up, and then I park it on your foot. And then while you're screaming because your bones are broken and I got the little penny on my toe, I'll say, wait a minute, why are you complaining? I have the same on my foot. Everything's pulled down with 9.8. I got 9.8 on my foot, you got it on your foot, right? Clearly, the bus is pulled down more. And yet, if I were to drop the school bus and the penny, they hit at the same time. Why? And basically, if that sounds a little strange, that maybe the bus being pulled down more should hit first, it's because you have an incomplete picture of what's going on. What you're saying is, yeah, I think the bus should hit first. You're saying more force is more acceleration. The bus is pulled with a lot more than the penny, and therefore it should race down and hit the table. Now, technically, the statement more force is more acceleration is correct. But that's not all that determines the acceleration. There's a piece of the puzzle that's missing to explain why the bus doesn't hit first. Can you think of it? I'll give you a second. Okay, maybe you said, we also need to consider the mass because the acceleration is not only about force, it's also about the mass. And so if I take the penny and the school bus definitely has more force, more acceleration, but it has also more mass, less acceleration. So the bus has something force that makes more, but it has something mass that makes less, and in the end those effects cancel. And that's the complete picture. You need both parts of Newton's law of force and mass. So this is a numerical calculation that shows that example. So let me give you a moment. I'll pause the video for you to copy this down. Okay, so what we've got is a 0.1 kilogram mass and a 5 kilogram. So this is 50 times as more massive. And so I draw the force of gravity. If I hung 0.1 kilograms on an electronic spring scale, it would record 0.98 newtons. 5 kilograms would record register 49 newtons. This is the Earth pulling down on the two objects. So the acceleration is that force over the mass. When you do 0.98 over 0.1 kilograms, you get 9.8. If you do 49 over 5 force over, you also get 9.8. So bigger and bigger create the same ratio. And this little equation here tries to show that conceptually. If we have a small force over a tiny mass, when you do that division, you get 9.8. Same as if you had a big force over a smaller mass bigger than before, but smaller than the force, you still get the ratio of 9.8. So everything accelerates at 9.8. So that's the complete picture. Okay, it's not because everything is pulled down equally, it's because some things are pulled more, but they have more mass. So now we say, okay, everything hits at the same time. Let's do another experiment. Oops, the book hit first. And then we say, well, looks like that statement that I said before is incorrect. But it's not, because what I'm ignoring and what I'm missing in the analysis here is that the force of air resistance. So now when air resistance is significant, it makes the paper lag behind. But if I could remove the air resistance, I could make these fall at the same rate. Let me show you. I'll put the paper underneath. All right, and you're probably saying, well, that's ridiculous. The book pushed the paper down and it was slower. All right, well, let me do this. Let me put the paper on top of the book and drop it now. Now, if it really is that this lags behind because of the effects of gravity and not because of the air, we should go like this and this should go separate. But if I do this, oops, let me try it again. It curled up a little bit. Okay, so. Together. And the reason why is because the book plowed the air out of the way, and now this didn't have air resistance on it, and it kept up with the same acceleration. Or I could do this. I could make this more aerodynamic, okay? And now they pretty much fall at the same rate. Let me show you that again. I think I didn't do a good job dropping. So there we go. All right. So what I'm going to do now is I'm going to show you the effects of air resistance. And I'm going to do that in a little PowerPoint. So we haven't jotted this down yet. That's going to come later. So let's see. There we are. So this is just a little, I took clip art, so it's not the greatest diagram, but I've got a little girl in a hot air balloon. That's basically what this is supposed to show. And while she's sitting in the hot air balloon, the Earth's pulling her down with m times 9.8. So if she's 50 kilograms, 490 newtons, something like that. The hot air balloon floor is supporting her with the same 490 newtons or whatever. And so the net force is 0, and therefore the acceleration is 0, and she's happily floating in the balloon at rest. What I'm going to do is now go over and press the button and release this. It'll be animated. It'll show what happens when she jumps out of the hot air balloon to do like a skydiving adventure. So hold on. So she jumps out, and you see the balloon force disappears, and now we've got gravity. And we had the acceleration in 9.8 as I talked. But as soon as she starts going, the air resistance now is in the backwards direction, reducing the net force and reducing the acceleration. But as you go faster, air resistance gets larger. It's not like the old friction that we learned about. So she goes a little bit faster, and now we have more air resistance, even less net force, even less acceleration instead of 9.8. That means she goes faster, gets even more air resistance, even less net force, even less acceleration, but she speeds up some more, so she goes a little bit faster, maybe to 59. Notice this gets bigger, and so even less net force, even less acceleration. And then what happens, eventually, she gets going even faster, getting even more air resistance, and then something special happens. The air resistance matches her body weight, and so we have a net force of 0. the Earth's pulling down maybe 500 newtons, and the air is pushing up with 500 newtons. And that means zero net force, zero acceleration. And again, people who don't understand physics well look at this and say, oh, she's floating. No, that's possible that she's floating. But she could also be falling at a constant velocity. As long as she's not speeding up or slowing down, that's balanced forces also. And so she's going at terminal velocity, this is like over 100 miles an hour, and she will never go faster. Even if she falls another mile through the air, she still maintains this 62 meters per second. And of course, we don't want that to happen because then she's going to hit the ground. So of course, she packed a parachute. Now let's see what happens when we take a parachute, and now it's like this paper falling, but it opens back up, okay? And so we had little air resistance to more air resistance. So that's the thing about air resistance. The faster you go, the more you have, and also the bigger you get, the more you have. So the parachute opens, and what you're going to see is this force grow up and become very large. And then people who don't understand physics will say, oh, that means she's going upward now because we have more force. No, she's going down, going to have more force in the backwards direction, means slowing down. Still going down, force this way, slowing down. So that's what's going to happen. Parachute opens, and you see the enormous air resistance. So now she's got an acceleration of 50 in the opposite direction, so the velocity becomes less negative. And as she slows down, the air resistance gets less, and so she still has an upward acceleration, so she slows down some more. And then what happens eventually, she slows down, and this gets shorter and shorter, and these match again. So she's going at a new constant speed with zero acceleration, a new terminal velocity of just 3 meters per second, lands on the ground gently, and she's okay. So that's the physics of skydiving. Okay, so let me just shut this off, and we will now look at the notes here involved. Okay, so go ahead and jot this down. Okay, so she jumps out with zero velocity, and let's take it a 5 kilogram mass just to make the numbers easy. You multiply by 9.8 and you get the 49 Newton force. When you do 49 over 5, you get acceleration of 9.8. Doesn't matter if we had 50 or 5,000, it would still be the same ratio. But as she falls, she goes faster, and now we get a little air resistance in the back. This says 10 newtons, 49 newtons. So what's the acceleration when she's going 30? And we could put a minus sign if we want for the downward direction, but I'm just looking at the magnitude, so I'm going to leave the minus off. So we do F net is the forward force minus the backwards force over the mass, and instead of 9.8, she's only speeding up at 7.8. So less acceleration, but she's still going faster, faster. So instead of going 30 and then 39.8, 1 second later she goes to 37.8. Still speeding up, but at a slower rate. This is an example of a non-constant acceleration, okay? Then, so she goes faster. When she goes faster, there's more air resistance, even more than before, 10 to 30. And so now when we do F net over m, forward minus backwards, we only get 3.8 acceleration. So she speeds up some more. Now while I'm erasing, making room, go ahead and jot. I think I've maybe already paused, but if I didn't, I'll create another pause to give you a chance to catch up. Okay, so then what happens is maybe at some 60 meters per second, whatever that is, some speed, eventually what happens is the gravity, the 49 newtons, still the same, is matched by the force of air resistance. This is now acceleration equals 0. And that doesn't mean we're at rest. Remember, we're still moving 60 meters per second. This is called the terminal velocity. Okay? the point at which you no longer speed up or slow down, you fall at a steady pace. Then if the parachute opens, what happens is that force of gravity is now more than counteracted. The F air might be like maybe 100 newtons in the upward direction. And so the deceleration now would be that's 5110.2 meters per second squared. That's again a deceleration, okay? And so that is slowing down, and then eventually we reach maybe a new terminal velocity of maybe 5 meters per second. And then here we have force of gravity 49 and air resistance 49 newtons also. Again, acceleration equals 0. The v is not 0, it's 5. This is a new, I'll put TV for terminal velocity. So let me create a pause to allow you to catch up. Okay, so the point is that when things fall freely without air resistance, everything, the ratio of F over m is 9.8. No matter big, big, small, small, you get 9.8. When air resistance is involved, the acceleration can be less because of the backwards force. So it might be like 7.8 or 5. And then, of course, when you're falling at terminal velocity, what happens is your gravity is matched by the air resistance. If you're a 100-pound person and you're falling at terminal velocity, air resistance is 100 pounds. If you're a 500-pound person falling at terminal velocity, air resistance is at 500. Equal forces and you fall at a steady pace, terminal velocity. All right, so that's it for today. I hope you enjoyed the video. I'll see you in the next physics video.